Welcome back. This is the very first video on the topic of gas laws. Now, you're familiar with both of these situations. One is a hot air balloon, and in the second picture is a person cooking at a high altitude. So why does an hot air balloon needs the hot factor? Can it survive without it? Or what makes the hot factor a key role in a hot air balloon? Or how does higher altitude affects the cooking process? Okay. Now, if you see, both of these questions are so open-ended. Okay. Now, I have modified the second question: how does higher altitude affects the cooking process? Typically, this question is written as, does the food cooks faster at higher altitude versus at sea level? Okay, I've modified the question to actually incorporate more meaning into the question itself. Right? Hopefully, by the end of this topic, or maybe the next big topic we will learn, which is colligative properties, you might be able to answer some of these questions even more convincingly, but then you can always Google it up, but then I want you to explore the answers to these questions on your own. All right? If you know the answer, great. Gas laws. First, we need to know what is the gas. Gases are nothing but particles that are moving around very fast inside the containers in which they are present. That's the most simplest example or simplest definition I could find for gases. Okay. Now, when we say particles are moving around, obviously they're going to collide with the walls of the container and with another particle in the process. Okay. And when many of these collisions happen over a period of time, it results in a pressure, right? That's why when you blow an air balloon with just regular air, air is a gas because it contains particles. The more air you put in and then you seal the balloon, it feels more rigid, because the more particles you put into that balloon, the more they collide with another particles and with the walls, the inner walls of the balloon, which results in a pressure. Okay, that's why the more air you put in and seal the balloon, the more rigid it feels, because you've now put in more particles, and in the process you've also increased the pressure within that balloon. Does that make sense? So there's three things that are critical when it comes to the pressure that's inside a container containing any gas. It doesn't have to be just air, whether it's carbon dioxide, nitrogen, oxygen, whatever be the gas that you're interested in. The pressure within that container depends on three things. One of it, which is number of gas particles. As I've already said, you can blow 4 or 5 different balloons with purposefully putting less and less air in each of the balloons, and then you seal the balloons. Obviously, the one where you put in more air will be the more rigid of the 4 balloons, and then the ones with less air usually would be a little bit floppy, right? So number of gas particles, assuming you have the balloon is the same volume, right? It's depending on how much you blow up. So if you have more particles, then you obviously have more pressure. And then the volume of the container. If you take a huge container and put very little gas, or you take a small container and put a lot of gas, the one obviously that's very small and a lot of gas would have more pressure, right? Because particles, only when they collide with each other, can generate pressure. If the volume is too large, what I'm trying to say here is, say you have two containers, right? One is big and the other one is very small. Okay, you can even think, say you've now changed the volume and you seal it, you put the same amount of gas, so say 4, 5, same 5 particles in both of these, because the volume is so small, the particles are constantly colliding with each other. So this will have more pressure versus the one that's bigger. So volume of the container is a key factor. And then the average speed of the particles. Now, in this case that I just drew above, there will not be any difference in terms of the speed, because speed becomes a key factor when you heat something or cool something, which means temperature is a key. So the third factor, which says average speed of gas particle, really is referring to the temperature of the medium, okay? So kinetic theory of gases. Now, I must say that you do not have to memorize it over the course of this material. This would become almost, easier for you to remember. But if it needed, yeah, you can go ahead and memorize this. A couple of these have already been mentioned to you. Kinetic theory of gases. In particular, we're going to focus on the assumption that makes a gas from a rare gas to an ideal gas. Okay, sorry, a real gas to an ideal gas. Okay, particles are constantly moving, which we've already seen. Attraction between particles is negligible. That is, particles collide with each other and then they go in different directions. It's called chaotic motion, which you can see in the picture, that 2 particles collide and then they're moving in their own direction. It is random. It's entirely random. Particles collide with each other and then the walls of the container. Okay, plenty of space between particles. You can see that the space occupied by the particle themselves, which is just this. Okay, this is just the particle. It's called a point mass. Okay, this is the volume occupied by just a single particle. Look at the size of the container. It's massive. So what that means is all of this is empty space. Okay, there's plenty of empty space between particles. And then this is what I was referring to, the average speed when it comes to the pressure. When I said pressure is directly related to the speed, which speed is nothing but kinetic energy. So kinetic energy is directly proportional to temperature. That is, if you heat, particles move faster. That is, pressure, temperature is directly related to the speed of a particle. If you heat up a container, particles move faster, more pressure. If you cool the container, then particles move very, very slowly, resulting in very little collisions, means less pressure. And collision between particle is completely elastic. What do we mean by elastic? Is they collide and then they move. They don't stick to each other. Okay? So the 2 assumptions that turns a real gas into an ideal gas is attraction between particles is negligible. That is actually related to the idea of elasticity. Okay? If there is attraction, then the particles would stick to each other. Only particles that are non-attractive will tend to collide and generate a chaotic motion, which is what we need. And then there's plenty of empty space between particles. All right. Now, ideal gas is a behavior that's obtained usually at moderate temperatures and moderate pressures. I say moderate because there's no certain value. But if you increase the temperature way too high, or you drop the pressure way too low, this is referring to extreme high temperature and extreme low pressure, then the ideal gas behavior is lost and ideal gas becomes a real gas. All right. Now, these are all the various gas laws we would learn in the process of learning, trying to understand the various property of a gas. Okay, so you got Graham's effusion law, Dalton's law, ideal gas law, Gay-Lussac's law, combined gas law, Avogadro's law, Charles and Boyle's law. Okay, all this may seem like a lot, but actually it's very, very simple. Okay, and I think this is one area where most of you would like. And then this is an ideal gas law. You do not have to memorize this. This will be in the appendix. PV equals nRT. It's very important you understand the units. Okay, because pressure is expressed in atmosphere, ATM. Volume is expressed in liters. Number of moles is moles. Gas constant, we would look at in the next screen. There's 2 different values for gas constant, and I tell you when to use which one. And then the temperature is in Kelvin. Okay, we'll come back to the actual equation and the significance later in the course, but I want to say that everything we're going to learn is based off of this single equation, how it's modified. Okay, the basics. Now, a great deal of information covered throughout this topic of gas laws. 98% of information you do not have to memorize. It will be in the appendix. I will let you know as we get closer to actually doing this in class, which will not be on the appendix. Okay, these two information are the gas constants, which is R. They're two separate values, and these both will be in the appendix. I can tell you that right now. Now, my high school or college teacher never told me when to use this. It's always a pain. So you use the top value if volume is not a variable. If that means your equation does not contain volume. Use the bottom value if your equation contains volume anywhere in the picture, then you use the bottom value. Okay? Again, temperature must always be expressed in Kelvin when doing calculations. If your equation does not contain temperature, then you do not have to make any conversion to the other variables like pressure, volume, and stuff. You can leave them as it is. But if temperature is there, temperature must always be expressed in Kelvin before a calculation has to be performed. So if your value is in Celsius, you add 273 to it. If your value is in Kelvin and I want you to get it in Celsius, then you subtract it from 273. Okay? And then 1 atm is equal to 760 millimeters of mercury. Again, you do not have to memorize. Any of this information shown so far will be in the appendix. So these are conversion factors for pressure. And then I want you to practice. Convert 30 degrees to Kelvin, 373 Kelvin to degrees Celsius, 0.5 atm to torr, and 250 torr to atm. This is algebra, okay? And this, I have to warn you, 175 is an algebra intense course. So you must learn how to convert units. That's very, very important. So for instance, say I give you 25 degrees Celsius and I want you to convert it to Kelvin. All you do is 273 plus 25, that's 298. As I said, whenever temperature is used, it must be converted to Kelvin. And as we work out problems, I'll tell you when to convert other things. But for the most part, every time you see temperature, it must be converted to Kelvin. Okay. Pressure and volume, not so much, except one special case, which we will talk. But temperature always must be converted to Kelvin. And again, you can do this. So for instance, say I want you to convert 0.6 atm to torr. Again, you start with 0.6 atm as your starting. So that's your starting for a 1, like you always did. And then we know the conversion factor is 1 atm is 760 torr. So 1 atm goes on the bottom, 760 torr goes on the top. So it'll be 0.6 times 760. It'll be 456 torr. Okay, so I want you to practice these 4 conversion factors just to enforce the idea of the basics that's pertaining to gas laws. But when I see you back, we're going to go ahead and work each of those different laws that I showed you earlier in the previous screen. All right, so stay tuned.